Hello friends, welcome to our new lecture related to signaling. I'm sure this lecture will be of great interest to you and this will give you a complete idea about the evolution of signaling in telecommunications network. So let's start. First, we should be deciding the objectives that we'll be able to achieve by the end of this lecture. So by the end of this lecture, you will be able to identify the main differences between the access and trunk signaling in the circuit switch networks. Basically, there are two main classification or main two types of signaling that is based on the access and the trunk part. Then later on you will be having a look how the access signaling is being implemented in the PSTN, ISDN and the PLMN networks. So once we study the access signaling, then we will be having a look into the trunk signaling and what are the different types of trunk signaling which are mainly classified as channel associated and common channel signaling. And then we will also be having a brief look into the SS7 signaling and its advantages. However, if you want to have a deep look and the structure of the SS7 signaling, then you can refer to our separate two lectures for which I can put a link into the description of this video and you can refer to that. So let's start. So we know that there are basically two main types of signalings in the networks which are referred to as access signaling and the trunk signaling. So it is also necessary to distinguish between the signaling for different bearer networks. Those are PSTN, ISDN and the PLMN networks. That how the access signaling is implemented in these different types of networks. In case of access signaling, we will be having a look into the subscriber line signaling and the DSS1, which is mainly referred to as digital subscriber signaling system number 1. And in case of trunk signaling, as I already indicated, that it is mainly divided into channel associated and common channel signaling. So let's have a complete picture of the signaling in the telecom networks. Basically, the signaling is mainly divided into two parts, that is the access signaling and the trunk signaling. Access signaling is basically related to the subscriber signaling, which in case of PSTN networks is mainly based on the DTMF subscriber line signaling system, and in case of ISDN and PLMN, that is the digital networks, it is basically the digital subscriber signaling system number 1, which is called the DSS1. If we talk of trunk signaling, then trunk signaling is mainly divided into two types based on its structure and construction, which are called channel associated and common channel signaling systems. The channel associated signaling systems have evolved from signaling system number 5, signaling system R1 to signaling system R2, which mainly have been used in the PSTN networks. While if we talk of common channel signaling, then there have been two major variants which are called the signaling system number 6, which mainly has been used in the PSTN networks, and the signaling system number 7, which is being used across all types of networks, that is PSTN, ISDN or PLMN networks. So this picture is basically going to give you a complete end-to-end visibility of the signaling types, uh, different variants, and how they are being used in different telecommunication networks ranging from PSTN, ISDN to PLMN networks. So let's start with the access signaling. And we start with the subscriber line signaling in the PSTN networks. Signaling on the analog subscriber line between a telephony subscriber and the local exchange is performed by means of on-off hook signals. That is when this customer on or off hooks the cradle on the handset of the handset, then how the digits are being dialed, then there are different information tones that are being extended like the dial tone, busy tone, etc. Then there are certain announcements as well. and the ringing signals through which the customer judges whether the B party or the called party has been engaged or has been informed or not. I think this picture is going to give you a very good picture what we have learned earlier in this slide, that whenever the subscriber off hooks or uh, picks up the cradle, then off hook or seizure signal is sent to the local exchange. Here in this diagram, we can see two subscribers, the A subscriber and the B subscriber, which are connected to the same local exchange. So when the A subscriber off hooks or picks up the cradle, then a seizure signal is sent to the local exchange and a dial tone is sent to the subscriber to make the subscriber realize that he or she can dial the digits. So when the customer dials the B party number, then these digits or these information signals are received at the local exchange, which in turn uses its database or its intelligence to make the call to the B subscriber and sends a ringing signal to that. That ringing signal or that contact is also extended to the A party to make the A party realize that the B party has been contacted in terms of the ring signal. There is a certain complexity that how this ring signal is being generated. So in this case, the B subscriber will be through some sort of electrical signal to make the ring on the handset, while in case of A party, it might be a dial tone type thing of sort of information that is extended to the A party. And once the B party answers the call, then or some sort of equipment is connected, then it might be transfer of information depending upon the speech, data, or facts, whatever bearer information is there. And once this data transfer or speech is concluded, then both parties performs the on-hook process and the call is ended. Now let's have a look at the digital subscriber signaling system number one that is used in the ISDN networks. DSS1 is the standard access signaling system used in ISDN and is also called a D-channel signaling system. D-channel signaling is defined for digital access only. The signaling protocols are based on the OSI reference model layers 1, 2, 3. Consequently, the signaling messages are transferred as data packets between the user terminal and the local exchange. So I hope this brief information is going to give you a very good idea that in case of DSS1, basically data packets are being exchanged between the user terminal and the local exchange, and it corresponds to OSI level 1 to level 3, and it is basically called the D channel signaling. Like you can see, you can have a better understanding over here that how the ISDN terminals, it can be a desktop, it can be a telephony machine, or it can be a printer that is connected to a network terminal point, connection point, and then it connects further to the local exchange. And on the bearer part, uh, the digital messages or the data packets are exchanged, which can have different information related to bearer capability, the address of the called party, which are being mainly contained in the setup message, the call reference, and specifications which guide these messages are referred in ITU TQ931. So here the example that we can refer to is of two bearer channels plus a D signaling channel. These two bearer channels can be of 64 kbps, while the signaling channel is normally referred to as 16 kilobits per second. So this signaling normally on the subscriber side comes in form of the 2B plus D, but it can be 30 bearer channels as well. The 2B plus D mechanism is basically referred to as basic rate access or basic rate interface, while the 30B plus 2D or 30B plus D is normally referred to as primary rate interface or primary rate access. In this diagram, you can have a better understanding of this uh, DSS1 signaling, in which two N terminals or the two digital terminals are connected to two local exchanges separately, while these exchanges are communicating through trunk signaling, which we will be discussing further in these slides and is called the SS7 signaling. So when the A terminal sends a setup message to the local exchange, then based on the information that is being carried in the setup message, as we saw earlier, the setup message can have a variety of information elements in it, based on which the local exchange performs a contact to the peer exchange to establish further subsequent connection to the B party. So, meanwhile, the local exchange sends a call proceeding message to the A terminal that the call is being processed and your request has been received. So once the alert message is transmitted to the B party, then same alert information is passed on to the A party to make the A party know that the call has been established and is in the alert phase. So once the call has been answered or is connected at the B party, then same connection message is sent, or the bearer is established between the A and B party, and the communication takes place. And once the both parties disconnects the call, either the B party or the A party, then the release process takes place and the call subsequently gets released. So this was the case that we have just seen. It was in the PSTN and the ISDN network. So let's have a brief look about the access signaling in the PLMN networks as well. Actually, both analog and digital systems are provided for access signaling in PLM. Like we can take the example of GSM as an example of a digital system. Basically, GSM is a digital system. The access signaling is executed between the mobile station and the radio base station, which we normally also refer to as BTS. The signaling system is based on DSS, also used by ISDN. So we can refer to over here that there are basically two different stages of the signaling when a mobile station or normal handsets communicates with the BSC or the base station controller. One is the air interface and the other is the line interface or the wired interface. The wide interface between the BTS and the BSC is called the simple D channel signaling, while on the air interface it is called the LabDM, that is, which is the modified link access protocol on the DM channel. So here also the digital signaling is happening on between the MS and the network. Signaling is of course needed when a mobile terminal makes a call. So now, like we are going to have it that till now we have just seen that signaling is only happening on the access side. So is it only this? No, because like even during a call in progress, different types of signals may be exchanged with the BTS, like for the handover, uh, like when the subscriber is going from the coverage of the one BTS to another. So handover is another type of signaling. So signaling is also needed when the mobile terminal is switched on but in idle state. This is because the mobile station can move around the cellular network. The HLR, it needs to communicate with the HLR, therefore have to be updated as soon as the mobile terminal reaches the new geographical position, like it moves in the telecom network or across the different mobile networks and performs the location updates. Then it needs to communicate with the network and performs the signaling. So this function is known as the roaming and is of course important. So we just have seen that in addition to the access signaling, there are different types of signaling in the network, like for the roaming part or for even for the handover part on the access signaling as well. There is a requirement or there is a need for another type of signaling which is not related to circuits. So these all signalings that we have just referred are not related to circuit signaling. So there is a need for another type of signaling which is not related to signaling, which is not related to trunk signaling. Uh, So, just emphasizing right now that we will be requiring another type of signaling that is not related to trunk. Let's move on to trunk signaling. Once we study the trunk signaling, then we will check that how this non-circuit related signaling is also being handled in this. So, in trunk signaling, the general associated signaling. Uh, basically evolved from the ITU-T standards. Typical example of such systems which are still used globally in some of the networks are signaling system number 5, R1 and R2. These systems were originally designed to mainly support ordinary telephone connections and related additional services. So the term channel associated signaling indicates that the transfer of signals is very closely associated with channel, which in this context means the traffic communication channel. Like as the name suggests, that channel associated signal is basically associated or travels on the traffic communication channels. Like we can take an example of the pulse code modulation system, the PCM, which has basically traffic slots for 1 to 15 and 17 to 31, while the traffic slot 16 is used for line signals. So 1 to 15 and 7 to 13 are basically register signals. Those are used for register signals or traffic channel signals, while the time slot 16 is used for line signals. Here you can see over here that in case of PCM, normal standard PCM frame, the time slot 0 is used for frame synchronization, 1 to 15 are used for register signals, which are also called the traffic channels. 17 to 31 are used again for register and traffic channels, while 16 is related to the line channel signaling. There are other PCM standards as well, like in case of USA and Japan, the system that is being used is based on the 24 time slots per frame. So in that case, what happens is that in a 24 channel system, one bit in each time slot in every 6 frame is allocated for line signaling. Register signals are transferred in the same way as in the case of the normal PCM 32 system, which you can also refer to as PCM 30 system as well. The reason for calling it as PCM 30 is that it contains the 30 register or traffic channels, while the two channels, one is used for synchronization and one is used for line signals. Then there is another terminology which is called the in-band and the out-band. So how they differ is that, like in certain systems, the messages are exchanged in terms of the frequencies which belongs to the speech frequency. The speech frequency we already know that it lies in the range of the 300 to 3400 hertz. So whichever signaling message passes using the frequency between this frequency range or the speech range of 300 to 3400 hertz, then it is called the in-band signaling. While if some signaling is beyond that range, like we can example of like 3600 to 3850 hertz, then that signaling is basically beyond that speech range and is generally referred to as out of band signaling. While in band signaling generally is of the range of the 2.4K to 2.8K. So I hope these two terminologies will also be used in other lectures as well. So for in band and out band, you will be able to get the concept of this signaling in case of the PCM system. So, what line signals are meant for? So, as the name indicates, this type of signal is related to the line. The line is an old word for traffic actually. So whenever we are referring to line, then it means traffic. The information carried by the line signals is mainly the same for all calls. Examples of line signals are like for idle line, seizure of the line, or seizure acknowledgement, B answer, clearing, release, line blocking, charging pulse, etc. So these are basically related to the traffic channels. Line signals can be sent or received during the entire call, even when a line traffic channel is idle. A line signal called idle line is usually sent continuously for that channel. The line signaling is handled by specific devices and functions in the exchange and must be allocated for each trunk line using a channel associated system. So what are the register signals? Register signals are basically control signals which control the setup of a call through all connected exchanges. These are basically unique to each call. So these are basically control signals, and when they are used, like to have the information for the call setup phase, like what is the call number, what is the calling party category, the either the B party is busy or idle or things like this, and what is the A party number in certain cases for the CLI representation. So these register signals are basically meant for controlling the setup of the call. So here you can see like the how the line signals and the register signals are being used for a call setup. Again, the same scenario as we discussed earlier. Two subscribers connected to two different local exchanges, and when they perform the off hook, then access signaling is going to happen. And when between the two exchanges, when there is going to be a seizure of the trunk, then there will be a line signal, and once the call setup information is being exchanged, then there will be register signal. Call setup exchange information relates to the dial number, the status of the B number, and uh, the information when the call is being answered, then it's related to the uh, again the setup information as well. And once the call is being released, then again the channels are released using the line signaling. So right now, just a side information that what are the different terminologies as I introduced the inbound and outbound terminologies. Then there are certain code senders and code receivers as well in the old signaling system of R2. Code senders and receivers are basically the signaling processors. Those are being used in the local exchanges, and they can be used for multiple sessions as the signaling just not kept on going, and they can be connected to different end devices. So right now we have seen that in case of all these traditional signaling systems, in fact have a number of annoying limitations such as the restricted capacity, slow signaling procedures, different setups, inflexibility when it comes to meeting the new signaling requirements. So these limitations are obvious taking in consideration that the systems were originally designed for analog telephony. The main issue is that these systems have been designed for the analog telephony, and we need to have certain signaling system that can meet the requirements of the ever increasing or ever evolving telecommunication network. So based on these requirements, the common channel signaling system, which had the approach and which had the flexibility of faster and more flexible signaling system as compared to the channel associated system. The idea was to design a signaling system that would better meet the new requirements that the market placed on the services provided by telecom operators. So the result of this development has been the uh, common channel signaling system in which the data packets are exchanged between the two exchanges, and we will further look into it. So, as the name suggests, the system was designed for use of common data channel signaling, which would exclusively serve as carrier of all signaling signals required by large number of traffic channels. This is why this system was defined as common channel signaling system. This signaling system described above was specified with CCITT in 1980 and given the name of SS7 and was intended for national as well as international digital networks. So, like there has been evolution on the SS7, and currently it is being used across PSTN, ISDN, PLMN, the public land mobile networks, and the intelligent networks as well. So, what are the different main advantages and features of the SS7? SS7 is basically highly flexible in the matter that SS7 can be used for many different types of telecommunication services. It is used for setting up and releasing the connections in traditional telephony and data communications, while in mobile telephony and data communications as well, for the provisioning of ISDN services and many other applications. SS7 is also used for interchange of data between the databases, for example, MSCs and HLRs, VLRs and HLRs, high capacity. A single signal link can support several thousands of frontline high speed. It is very high speed at the same time. Setting up a call through a number of exchanges takes place less than a second, very quick in terms of milliseconds, depends on the processors and capability. It is highly reliable at the same time. The system contains powerful functions for eliminations of disturbances. It is highly reliable. There are several procedures defined into that. If you want to refer those procedures, you can refer to our SS7 signaling lecture, which discusses these uh, reliability mechanisms and protection against failure scenarios. So you will be able to understand those scenarios in detail and what are those scenarios. So, and it is economical at the same time. The fact that one and the same signaling system can be used for wide range of telecommunication services, so makes it economical. And also it makes it more suitable for the researchers, more suitable for the suppliers to use this system in their products for future-proof solutions. Besides, SS7 systems are much simpler and require much less hardware than the old signaling systems. So we can say that SS7 can handle both circuit related signaling and non-circuit related signaling. As we discussed in the earlier of the lecture, that basically our requirement is not just limited to circuits or the access signaling. There can be several scenarios across the telecommunication networks or the requirements of the application, where we just not have to deal with the circuits. We have to deal among the databases. We have to deal with the uh, intelligent networks logic. So for that, we need to have a signaling system which can handle those requirements, and those basically fall under the category of the non-circuit related signaling. So SS7 can very flexibly handle such requirements, and this circuit related signaling means that signaling sent in order to support a call establishment on the access part, while non-circuit related signaling refers to the requirements of the applications. So this picture is going to give you an end-to-end picture or end-to-end idea that how different entities communicate between each other in a telecom network and what are their requirements. Like if we see that if we have at the top layer we have the international exchanges. International exchanges are those which connect the a country to different countries. These are basically meant for country to country connectivity. Then these international exchanges are connected to different GMSCs, the Gateway Mobile MSCs. Then they can be connected to the transit exchanges, the PSTN exchanges as well. So the requirement between these exchanges can be related to the trunk signaling, while the and also between the transit exchanges it can be related to trunk signaling. While in case of the mobile networks, there are other services as well which relate to the like the prepaid telephony or connectivity with the HLR, then that signaling requirements are basically fulfilled by the SS7 signaling, because these are not related to the any circuit. So for non-related signaling or for non-circuit related and circuit related signaling, SS7 can fulfill the requirements of the network to provide the flexibility, reliability, and speed. Uh, in all cases, SS7 is the prevailing signaling standard and is widely used across uh, the world. So now we are drawing near to the end of our lecture. So in this lecture, we have focused on the different types of networks that like in PSTN, ISDN, PLMN, how the access and the trunk signaling is being implemented. In case of we have also seen the cases of the DSS1, which makes use of the D channel, and in GSM networks we have also seen the excess signaling, and we have also seen that the signaling requirements are not related to the trunk, or we need to have certain circuit independent signaling as well, which are made